Essentially, what's important to realize is that with introducing confidential computing, we can have new types of digital interactions. Since data can always remain private, new forms of collaboration between parties that in the past could never have collaborated become possible. Enhanced model accuracy can be achieved by having access to more sensitive, more valuable data, and new economic incentives can be designed by having this data ownership system. Now, you might wonder, how is decentralized confidential computing possible? How can we build systems like this? Let's look at the history of confidential computing, the evolution essentially. So the first systems that come to mind that can be utilized in order to achieve these properties would be trusted execution environments. And so trusted execution essentially is the sort of, I would call it, legacy way of approaching confidential computing. So that relies on dedicated hardware that is being provided by trusted hardware manufacturers. And so this hardware comes with security and privacy promises provided by those manufacturers. And this hardware and those promises essentially is a result of a proprietary trusted supply chain that produces and distributes those hardware chips. And so the issue associated with this technology really starts with high maintenance and hardware cost, but essentially circles around a fundamentally flawed trust model. And what we are trying to build with decentralized confidential computing is a completely trustless architecture, an architecture that allows data to be held by the owner, yet be usable in model training, and so involving trust, and especially this kind of trust that due to a myriad of exploits, vulnerabilities, and attacks that have surfaced in the last years, really means that very valuable, very sensitive data cannot be exposed to these kinds of systems. And the data that I'm talking about really is highly sensitive patient data, for example, healthcare data, data that yields great value if it could be utilized for model training, but at the same time, if exposed to unwanted third parties, has great risks associated with this leakage of information. And so in order to not face situations like this, we can't rely on this technology that requires trust in a proprietary supply chain with many actors associated that have to be trusted. And so the approach we have to take is looking for distributed and mostly or purely cryptography-based solutions. And here you can see the workflow essentially of data processing using trusted execution environments. And here you can see how it's always a chain of single actors. So the trusted execution environments represents a single point of failure. And that has been the case for many years. And so one of the first cryptographic protocols that comes to mind would be utilizing zero-knowledge proofs for confidential computing or confidential machine learning. Zero-knowledge proofs are a family of cryptographic protocols that allow one party, a prover who has access to some sensitive information, to generate a proof by executing over the sensitive information and transmitting that proof to a secondary party. And that secondary party being convinced of the correctness of this execution without having to disclose the information. So it adds privacy and in the blockchain setting also scalability. The problem is that that's not suitable for what we're trying to achieve. What we're trying to achieve essentially is to take data that is distributed, highly sensitive data, and combine it together in training pipelines without having to share that data. And zero-knowledge proofs, at the end of the day, require parties that have access to that data to generate proofs, and we want to outsource this computation over highly sensitive data without requiring any single party to hold that data. And so the next kind of technology that comes to mind would be fully homomorphic encryption. And fully homomorphic encryption allows essentially what we're trying to achieve. The computation over encrypted data without requiring to decrypt it, which is very, very great and amazing. The problem with FHE really circles around its incredible practical limitations. So when comparing it to plain text execution times, and that's not comparing it to machine learning, we're faced with many orders of magnitude performance latencies. And so it's not uncommon to see 10,000 times slowdown of operations over the plain text execution times. And when trying to execute tensor operations, matrix operations with real number arithmetic, that becomes even more significant, these kinds of slowdowns. And so that's not only a question of latency, but it's also a question of cost. And so what we want to achieve is a system where developers and applications don't have to value data privacy and the economic cost of utilizing this data privacy. And the incredible slowdown of fully homomorphic encryption essentially comes from a subset of operations being incredibly expensive to execute, which requires frequent so-called bootstrapping when performing a lot of multiplications, which in training AI models, unfortunately, has to be done quite frequently. And so this technology, also by not allowing for selective disclosure, so to reveal information about some encrypted state, is unfit for what we are trying to achieve. And so the technology that we think is the perfect fit is secure multi-party computation. And secure multi-party computation, or MPC, allows a set of participants in a computation to jointly compute a function over distributed private data. And they're able to compute this function while all data that each participant inputs into the computation remains private. And it's possible to achieve something like this by utilizing secret sharing. So that's the core technology that secure multi-party computation utilizes under the hood. And secret sharing means that individual participants in a computation hold secrets which they want to use in the computation but don't want to share with each other. And what they do is they take those secrets, they split them into random shares that on their own don't communicate anything about the secret, and then they send those shares to the other participants. And only having all shares together, combining all shares together, can reconstruct such a secret. And so that's the core primitive using multi-party computation, that each participant that has secrets takes their secrets and creates randomized blinded shares and distributes those to the other participants. And then, once that has happened, each participant is able to perform local operations over the set of shares that each holds, and they're also able to perform communication-based operations over those shares. And at the end of this protocol, where each participant runs local computations and communicates with each other and runs communication-based operations, at the end, a combination of those shares takes place. And by combining together the resulting shares, they're able to reconstruct an output that can either be in an encrypted or decrypted form. And what we're doing is we are extending this principle with so-called threshold encryption, so to allow a set of participants to hold key shares to a decryption key essentially, and combining that with this secret sharing based multi-party computation, we are able to allow a set of computers to process any given encrypted state. Now, multi-party computation comes with trust assumptions. There's two kinds of families of protocols essentially, honest majority and dishonest majority protocols. Honest majority protocols is what we are familiar with from practical Byzantine fault tolerance blockchains, more than half of participants having to behave honestly, for example. And honesty in this case means not maliciously collaborating in order to undermine the confidentiality guarantees of the protocol. And so in our case, the honesty setting that we are working with is the dishonest majority protocol. So instead of having to trust that there's not some malicious set or some malicious subset in a set. In our case, it's really as long as not the entire set is malicious, so there's one participant that is not malicious, confidentiality is guaranteed. And that's the best trust assumption you can have in a distributed setting. Bare trust is involved. And so this makes this trust assumption scalable as well, because 1 out of n is an incredibly scalable trust assumption. And that's the setting that we're working with. And so within the Aarcium network, we have multiple MPC protocols, each fine-tuned essentially for a different task. So we have the Cerberus and the Manticore protocol, and Manticore is fine-tuned for distributed machine learning. As I said, we have the dishonest majority trust assumption, and we utilize semi-homomorphic encryption. What that means is that we essentially take efficient parts from what I described earlier, homomorphic encryption, and for the inefficient parts of FHE, we instead make use of recent advancements in MPC pre-processing protocols. And so we split the computation phase into 2 phases, a pre-processing phase and an online phase. And the pre-processing phase generates correlated randomness that is independent of the actual computation and inputs that should be performed within the online phase. And that, by splitting those phases and consuming this previously generated correlated randomness in the online phase, that brings the execution time of the online phase close to plaintext execution. And we extend this protocol with so-called cheater identification, which allows anyone essentially to identify any malicious behavior cryptographically. And adding this censorship resistance mechanism combined with a staking and slashing mechanism allows us to have Aarcium as a completely stateless computational network and use existing blockchains for consensus and state management. And so we have this permissionless network of nodes that run multi-party computations, and these get clustered into groups of nodes, into dishonest majority clusters, and those clusters then run individual computations. And each cluster gets associated with an MXE, an MPC execution environment. That's at the end of the day what the developer defines, and that's a virtual encrypted environment that exists on this network and can have encrypted state on corresponding ledgers, but not on our network on its own. So you can have encrypted state on Solana, on Near, on some L2, whatever, and the execution over that encrypted state that happens within Aarcium. And the orchestration of computations happens in a parallelized mempool. And so if we compare the workflow to what we had earlier, essentially what happens is that encrypted data is being turned into a secret shared representation, and this secret shared representation allows any set, any arbitrarily sized set of computation nodes from the Aarcium network to process this encrypted state in the way that is desired. And combining that with the dishonest majority trust assumption means that you only have to trust in such a computation that there's one node in a cluster that isn't maliciously collaborating with all other participants. And the way we think about it is that we can bring down this trust assumption to relative zero if you're a participant with skin in the game that can ensure that yourself are not maliciously collaborating with the others if you have an interest in not doing so. And so with Aarcium we have this generalized confidential computing network. Within we allow for every kind of computation, and so for that we have a dedicated compiler that allows arbitrary Rust code to be compiled for our network to be processed. At the same time we have a Python SDK that allows for the entire data science and machine learning workflow. It's possible to build confidential on-chain applications with Aarcium, and confidential off-chain applications. And one example would be building confidential machine learning with Aarcium. And so I talked about the Manticore protocol that we've developed a bit. What we achieved with the Manticore protocol is an increased numerical stability, and the difficulty really is when trying to do machine learning within MPC, FHE, or CK really is that the numbers you're working with usually are scalars or elliptic curve points, and you don't have access to native floating point number representation. So the struggle really is to build an efficient yet precise system, and we were able to achieve that. We have a very high numerical stability. So for large machine learning processes, we usually get above 10 to 15 decimal digits in precision. And we utilize a hybrid approach. So we combine different numerical representations within our protocol. So we have real number arithmetic, Boolean arithmetic, garbled and arithmetic circuits, and we can efficiently switch between those numerical backends. And for this we utilize modular lifting and truncation. And so we're essentially able to represent real numbers over integers. And for further optimization, we utilize a uniform approximation of the sigmoid function via Fourier series, and we employ oblivious data structures and oblivious sorting algorithms. And we can combine that with hardware acceleration and communication compression, and that really allows us to have really efficient machine learning in a distributed setting over distributed, isolated, sensitive data, and have the output models be precise. And what's possible to build with this technology is it becomes possible to have completely encrypted confidential training workflows. At the same time, the resulting model can remain encrypted, and inference and prediction within that model can be encrypted. And so it's really possible to build end-to-end encrypted machine learning systems. And our goal really is to make that as efficient and trustless as possible. Yeah, thanks for your attention.
Okay, thank you, Yannik. So, yeah, we can take one question if there's any question from the audiences. Okay.
Hi, thanks for the presentation. It's very enlightening. One of the questions is very open-ended. What do you think is the biggest problem that you're facing while you're currently in testnet?
The biggest problem for Aarcium, what we are facing, it's implementing all of the things that we have devised on a theoretical level, but actually being able to implement all of that.
Because you mentioned something about taking any arbitrary Rust.
Yeah, exactly. So I think what we are building towards, and currently what we have is this two backend system between which switching is possible. So we have this fine-tuned backend that I just described that is great for performing efficient tensor operations. And then we have the other backend that essentially allows for scalar, elliptic curve, and Boolean operations. And I think one significant step is adding an efficient ability to switch between those two backends, which should be done at some point on our roadmap, and then allow for direct access to large oblivious data structures as well.
So currently, are both of those running in every node? Is that how you're currently solving this?
Yes, but at the end of the day, the node is able to decide which protocol they want to use. So nodes can specialize. So if you're a node that has dedicated hardware, you can specialize on just running this tensor backend, because that makes more sense based on your hardware.
Thank you, Yannik.